Hi everyone. Welcome to this evening's live stream. So tonight I'm going to do, I think, like 9 questions on the electricity and magnetism that we've been studying this week. And some of these questions are pretty short, so let's just start, okay? So electricity is another fundamental force in the universe. It's like gravity, which is a fundamental force. And there's others, like there's the strong nuclear and the weak nuclear force, but we're not going to look at the nuclear forces at all. So we'll just study the electrical force next. And when you compare it to gravity, there's some remarkable differences between the two. So my first question, very simple question, is what are some of the differences between gravity and electricity? Okay, and one of the biggest differences is that the gravitational force is a pretty weak force compared to electricity. Electricity is a very strong force, whereas gravity is a very weak force. You may not feel that. You may think gravity is pretty strong, but that's because you're thinking of the gravity due to the Earth. Okay, but if you think about the gravity between you and, say, I don't know, like a book on your table or something like that, that force is very, very small. It's very difficult to measure. It is there. It is measurable by an experiment called the Cavendish experiment, but it's very tiny. Okay, so that's one difference, is that gravity is very weak compared to electricity, which is much stronger. And the other difference is that gravity is only attractive. Mass only comes in positive, and there's no such thing as negative mass. There's just positive mass, and it's like how much stuff is there. And as long as there's some stuff present, and there's two masses with substance, those two masses will attract. So gravity is always attractive and mass is always positive. Whereas electricity has two different types of charges, positive and negative. And if you have like charges, they will repel, and opposite charges will attract. Okay, so those are the basic differences between electricity and gravity. Okay, there was also electricity and magnetism, and they're actually the same force, but at first it doesn't look like it. Okay, so when we get to studying magnetism, you'll see why. And so a question that I could ask is like, what's some of the differences between electricity and magnetism? And well, let's start with the similarity. Electricity comes in two types, positive and negative. Magnetism comes in two types, north and south. But they'll also, like charges and like poles will repel, and opposite charges or opposite poles for magnetism will attract. So that's a similarity, but a difference is that they appear to be different forces on the surface, because north and south do not interact with positive and negative as long as the charges aren't moving, and that'll be the linking thing that we'll come up with later. Okay, so to summarize, electricity works with charges, okay, and whereas magnetism works with poles, okay, and charges being positive and negative, and magnetism being north and south. The other difference is that charges can be separated. So if you go down to some of the most fundamental charges, like of an atom, say a hydrogen atom, hydrogen atom's got a proton, which is positive, and an electron, which is negative. You can separate the two. Okay, that's called ionization, where you just blast the electron away from the proton, and you can have the electron by itself at one point and the proton by itself at another point. Okay, poles you cannot separate. Okay, and you say, well, what do you mean you can't separate them? So if you have a magnet where one end is north and the other end is south, and you break it, you don't get a north and a south. Each piece will have a north end and a south end. Okay, so that's different. Okay, so let me just describe that again. You've got a magnet, and it's north on this end, it's south on that end, and you break it. You think you have a purely north magnet and a purely south magnet. It doesn't work like that. Okay, the side that was say north, will stay north, and then the broken piece, the other side of it, will become the new south. Okay, so with the magnet, there's always a north and a south side, and if you break it, you just get two magnets, both of which have a north and a south. Okay, so that's different. Okay, so the way I describe that is charges can be separated, poles cannot be separated. If there's a north, there's a south on the other end of the magnet. Okay, all right, so there's another difference. Okay, and then number 3 is why is the normal force not a fundamental force of the universe? That's because the word fundamental, that's the key word there, fundamental. So normal force is touching force, and the reason it's not fundamental is, you ask, well, what's going on as the touching happens. You look down at the microscopic level and you realize that the touching is the touching or the interaction between atoms and molecules. And what are atoms made out of? What are molecules made out of? Positive and negative charges, okay? And so down at the microscopic level, the normal force is actually the electrical force, okay? And same thing with friction. I could have asked the same question. Why is the frictional force not a fundamental force? And that's because friction, when two things are rubbing, they're touching, but they're touching in a kind of a different way, as they rub against one another. But again, that interaction at the microscopic level is between positive and negative charges of the atoms, and again, it is fundamentally electricity, okay? So that's what this word fundamental means. It means, you might have a force, and at the microscopic level it has a particular characteristic, but when you go right down to the microscopics, you're going to find that what's interacting there is one of the fundamental forces, okay? And again, those fundamental forces being, it's either going to be gravity down there, or it's going to be electricity and magnetism, electromagnetism, or it's going to be the weak nuclear force or the strong nuclear force. Okay, so there you go. That answers that question. Okay, so let's start off with our first question, which is actually a numerical question, not a qualitative question. And if you have charges, and you have two charges, there's an electrical force between them, and an electrical force is either a push or a pull. Okay, that's what's meant by force. So if I give you the charges and how far apart they are, you ought to be able to calculate how much force there is between those two charges. Okay, so here's the question. A 3 nanocoulomb. Okay, so I should just mention that when it comes to electricity and magnetism, this next section, there's going to be a lot of very large units and a lot of very small units. So you need to know things like what is meant by milli, that's 10 to the minus 3, micro, which is 10 to the minus 6, and nano, which is 10 to the minus 9, okay? I don't think we'll have to go much smaller than that, but you do need to know those. And then the bigger ones, okay, there's like kilo, mega, and giga, okay? And you'll need to know those too, all right? And you've seen them already when, especially the larger ones earlier in the course. Okay, so let's continue. A plus 3 nano coulomb charge is placed at 3.5 millimeters from a negative 2 nano coulomb charge. What is the magnitude of the force? We'll calculate that in a second. And is the force attractive or repulsive? Okay, so with electricity, when the two charges are opposite, which is the case here, one of them here is positive and the other one here is negative, okay? When they're opposite, it's attractive. So the force is attractive. And how do you calculate that force? You use this formula right here, okay? Let me just check the chat for a second to make sure that everything is working fine there. See if people are on board. And yeah, everything looks fine. Okay, so all right, so let's do this problem. And what do we have here? Well, there's the formula. And so we have that the force is equal to, we've already decided it's attractive, okay? The force is going to equal K. And what's that K? K is the Coulomb constant, okay? It's kind of like the universal gravitational constant for gravity. This is the Coulomb constant, okay? And it's a number, and I would give it to you, but our tests are open books, so you could always just look that up, even if I don't give it to you in the context of the problem. Okay, so K is going to be this number right here, and there it is in MKS units. Whoops. All right, like that. All right, and it's let me just show you what the units are. It's Newton meter squared per Coulomb squared, and the meter squared will cancel against the meter squared that'll come up in the denominator there, and the Coulomb squared will cancel against the Coulomb times Coulomb in the numerator there. Okay, so we have two charges, so here's Q1 and Q2 like that. And so Q1 I said was 3 nanocoulombs right there like that. All right. And nano, what is that? So I just said it a minute ago, it's times 10 to the exponent negative 9. Okay, coulombs like that. And the other one is negative 2 nanocoulombs like this, okay? And I'll tell you right now, you don't really need that negative sign. And the reason you don't need the negative sign is because we've already decided that this is an attractive force. So, whether you put it in there or not, it doesn't matter. I mean, you'll get a negative F if you get that, but the negative or positive F doesn't matter. We're really worried about the magnitude, and so let's just drop it so that um, we don't have too many symbols floating around. And again, it's nano, so it's going to be times 10 to the negative 9 there, like that, divided by, and it's going to be r squared. That's the distance between the two, and that was 3.5 millimeters. Okay, and the millimeters is 10 to the minus 3. Milli is 10 to the minus 3. So let's get rid of that. So this is times 10 to the negative 3. Okay, and it's squared. Okay, so we need a squared there, like that. Okay, there we go. There's the formula. And I have the units in there. I'm going to take them out in a second, but I'm going to show you how they cancel. So let's start here. We have a Coulomb there, and we have a Coulomb there, and they're in the numerator, and they will cancel against this Coulomb squared here in the denominator of the units for K. Okay, so that Coulomb and these two Coulombs will cancel against those two Coulombs. Okay, and so that's that. And let's get rid of this. Okay, and then you've got a meter squared up here that's inside of K, and that's going to cancel against the meter squared in the denominator there, like that. So these 2 meters here will cancel against those 2 meters there. Okay, and again, because it's squared, there's actually a meter times a meter there, like that. And so you see that the only unit that survives is the Newton, which is what you expect for a force. Okay, so there we go. So I'm going to just put that Newton out here, like that. Okay, and now I should be able to copy and paste this into my calculator and get an answer. All right, I'm not sure that's right. Let me put another set of brackets in there just to make sure that everything is working out right. Yep, there it is. Okay, so this is going to equal, F is going to equal, like that. And of course, way too many decimals. We just want to round off to 3 significant figures. So the first non-zero is that one. So 3 significant figures would bring us to there. So let's get rid of all these. Okay, and there's your answer. But it's kind of ugly to have that many leading zeros. So let's move the decimal over. So if we move it over 1, 2, 3 places to the right, that'll give us 4.40 times 10 to the negative 3 newtons. Why negative 3? Because we moved it over 3 to the right. 1, 2, 3, like that. So negative 3. But negative 3 is milli, and so this is going to be, the answer will be 4.40 millinewtons. Okay. On a test, I would probably write it like that. Okay, and the reason is like, in the real world, or whenever you've got, like, you're working with these numbers in some field, then you're never gonna see, well, I wouldn't say never, but you would hardly ever see that. You would see this. Okay, so there you go. Pretty straightforward. And let me just say a little bit about the physics. The amount of force you get will, of course, depend on how big the 2 charges are. The bigger either one of them is, the more force you're going to get. That makes sense, okay? And the other one is it's inverse r squared, okay? And we saw the inverse r squared earlier with sound. That the further away you are, the weaker the sound, and it drops off not as the radius, like 1 over the radius, but 1 over the radius squared. And so, the further away you are, the weaker the force. Okay, and so that's all this formula is saying. Okay, and so there it is. All right, and all right. Well, let me see if there's any questions in the chat. All right, a couple of people listening in, and I don't see anyone asking any questions. Let me go on. Okay, so the next question is, by the way, there's not really much more that I would ask about this. To make this problem harder, not that I would do this, but just to give you an idea of where you could go with this, is that what if you had 3 charges? Okay, well, remember, forces are vectors, so then what you would have to do is you'd have to add these things as vectors. Okay, that's why my problems only have 2 charges interacting with one another. But if you had 3 charges, then one charge would see 2 other charges, and each of those 2 other charges would have a force, either attractive or repulsive. But remember, when you've got force from one and a force from the other, what do you do with the 2 forces? You add them. And adding two forces means adding two vectors. But I don't think we need to go there. But I just wanted to mention it in passing. Okay. Okay. So the next one is how many extra or missing electrons are there in the 3 nanocoulomb charge? So this is Q is equal to this. Okay. Now down at the microscopic level, there are particles, okay? And generally when a physicist says a particle, they mean something which is indivisible, okay? That used to be an atom. In fact, that's what the word atom means in Greek, is undivisible or uncuttable. But the thing is that atoms are cuttable, okay? You can break an atom and split an atom, okay? But you can't split electrons. Okay, and protons you can actually kind of split. I don't want to get into the physics of quarks, but electrons you can't split. There's no like half electron and half an electron. Okay, when you get down to that microscopic level, there are particles which will carry the charges. Okay, and what's carrying the charge in this is going to be electrons and protons, and the protons are heavy, so we're not so much worried about how many extra protons or deficit of protons there are. We're more worried about how many extra electrons there are, or deficit of electrons. When you like say you have a rubber balloon and you rub it on your hair, okay, and it gets a static electricity. What you've basically done is you haven't really moved the protons around because those are embedded in the nucleus and they're pretty heavy. You've actually moved the electrons around. So in these questions, we're usually asking how many extra or what deficit of electrons do you have. Okay, because it's a positive charge and because electrons are negative, all right, you actually have a deficit of electrons. So you're missing electrons. I put missing here, missing or deficit. So you don't have extra. If you had extra electrons, that is extra in terms of what? Like extra in terms of how many protons you have, okay? If you had more electrons than protons, then the object would be charged negative. If you have less electrons than protons, then it would be charged positive. But think of it this way. Maybe I could just give you a little bit of a diagram like this, okay? So, what am I drawing here? A bunch of positive and negative charges, okay? Like that. So you can see here, like I've got a bunch of positive and negative charges. And you say, well, how many positive charges do I have? 4. How many negative charges do I have? 4. So what's the charge of this thing? It's neutral, 0. There's 0 net charge. Think of it as a net charge, okay? If I have extra electrons, like suppose I embed an electron right there like that, okay? And you say, well, what about now? Well, now it's slightly negative because there's an extra electron, all right? And so that would be like a Q of a negative Q. But what if I had this? What if I was actually missing an electron like that? So now I have a deficit. I've got 4 positives, but only 3 negatives. Well, now you have a deficit, okay? Or you're missing some electrons, okay? And the whole thing would be net positive, and that's the situation here because that's why I put the positive in front of the 3. It's positive 3 nanocoulombs. Okay, so there we go. This is going to be missing electrons to give a net positive charge like that. Okay, and the next thing is how many electrons. So you can see just how many like that. Well, what is that? Well, basically it's going to be the total Q divided by the Q of 1 electron, okay? And usually we use the symbol E like that. I don't know what I used in the pre-recorded lectures, but the charge of just a single electron, sometimes we call it E. And you say, well, what is that charge? It's negative 1.6 times 10 to the negative 19 coulombs like that, okay? Let me just quickly check that number. I'm going by memory. Charge of 1 electron. By the way, what I'm doing right now is I'm just going to Google, and you just go to Google and you just type in charge of 1 electron, and 1.602 times 10 to the negative 19. Well, we'll just round off to 1.6, okay? So there you go. There's the charge of 1 electron. And I put the negative in there because the electron is negatively charged. And so let's see how this works out. So we have 3 nanocoulombs like that. All right, let's get rid of the plus because it's implicit. Okay, and nano is what? Well, we said it before. Nano is times 10 to the negative 9. Okay, so there we go. And divide that by this number right here. Okay. Now, I mean, I got the negative in there, but you really don't have to worry about it because we've already determined that this is going to be missing electrons. Okay, the negative that'll come out here will just be missing, but like I said, we've already determined that. Okay, and notice you have coulombs on top here and coulombs on the bottom, and they'll cancel, and it should, because what you're getting out of this is just a count, and there's no units associated with the count. Like if you say 5, like 5 extra electrons, okay, that's just like a number. It isn't a charge. It isn't. There's no units associated with counting things, and so that Coulomb there will cancel that Coulomb right there, and let's see how many extra electrons that turns out to be. Oh, I have a nice calculator where I can just cut and paste these, and I'll get an answer. There it is. Okay, and that's a deficit. Okay. All right. Now, it's kind of annoying that it didn't. You don't know how many zeros you are, but let's put some commas in there. That would be at the 1,000 mark. That's at the million mark. That's at the billion mark. Okay. So basically, all you need is a deficit of 18.75 billion electrons. Okay, to get a charge of 3 nanocoulombs. All right. So because the electrical force is a strong force, you don't need like a lot of extra electrons or a lot of removed electrons before you see an appreciable effect. Okay, and so, well, there it is. Okay, so how many extra missing electrons are there? Well, we are actually missing about 18 billion electrons. Okay, 18 billion is nothing. I mean, just think of that. A billion is 10 to the 9. Okay, what's Avogadro's number? 10 to the 23. So 10 to the 9 is like nothing compared to 10 to the 23. All right, it's very few atoms have to lose an electron in order to get you that 3 nanocoulomb charge. All right, let's continue. Okay, so the next thing I introduced was electric field. And what is an electric field? It's kind of like a gravitational field. See, the Earth's surface creates a gravitational field of 9.8 meters per second squared. Where is it 9.8 meters per second squared? All over the surface of the Earth. It's like a constant 9.8 meters per second squared. And because it's a gravitational field, okay, that means that any mass that you put inside of this field is going to have a force associated with it, and it's going to be the size of the force multiplied by the size of the field, mg. Size of the mass. Sorry, what did I say? I think I said it wrong. It's going to be the force is going to equal the size of the mass that you put within the field. So it's going to be the size of the mass multiplied by the size of the field. So that's what your mg is. How big is the mass? How big is the field? That'll give you the force. It's the same thing with electricity. If you put a charge within an electrical field, the amount of force on that charge is just going to be equal to the charge, the size of the charge, multiplied by the size of the field. Okay, and so I'll just write the 2 down. So for a gravitational field, which we studied last semester, okay, for a gravitational field, the force is equal to mg. Okay, m is the mass. That's the thing that carries the force. Okay, and g is the size of the field. For electricity, it's going to be F is equal to what carries the force? Charge. And what is the size of the field? That's E. Okay, so you can see the analogy there between the two. Okay, again, I mentioned that in the lecture, but this is what we want. Okay, so how big of an electric field, in other words, I'm asking you to solve for E. How big of an electric field do we need to exert a 20 micronewton? So I give you F, 20 micronewton force on a 3 nanocoulomb charge. So, okay, so Q is 3 nanocoulombs. Well, it's really simple. I'm asking you to solve for E, so just rearrange this like that. Okay, and F is 20 microcoulombs, like that. And Q is, divided by, Q is 3 nanocoulombs, like this. All right, and we want everything in MKS. So micro, what's micro? Micro is 10 to the minus 6. So replace that one with times 10 to the negative 6. Okay, get rid of that plus because, again, it's superfluous. And nano is times 10 to the negative 9, like that. Okay? And so the units for electric field are newtons per Coulomb. Okay? So let me write this on the next line here. It's equal to this. Let me get the units out of there. There's that. There's that. And it's newtons per Coulomb. Okay. And what's this equal to? Okay. Get this. E is equal to 6,666.66666666666. Okay, just rounding that off. I don't know. We could just round it off to 6,670 newtons per Coulomb. Okay, rounding it off to 3 significant figures. All right, so pretty simple, but a problem can be mathematically simple, but if you don't understand the physics, you don't know what to do. Okay, so again, if you've got electric field, charge, and force, they're related by that equation there. Okay, now what? Another electric force problem here. If a 3-gram mass has a plus 2 microcoulomb charge, what is its acceleration in a 500 Newton per Coulomb electric field? Okay, so the electric field, the units are newtons per Coulomb, because another way to think about it, one way to get at the concept of an electric field, it's like how many newtons of force do you get per Coulomb that you put into it. Okay, so if there's no charge in the electric field, it's there, but you don't even know that it's there because there's no force on anything. If you put a little charge in there, there'll be a little force. If you put a bigger charge in there, there'll be a bigger force. If you put a bigger charge yet, there'll be a bigger force yet. Okay, so the amount of force you get is proportional to how much charge you put in there. And as you can see there, the amount of force is proportional to the charge. Okay, that in this formula right here. Okay, so here I'm going to put a charge in this electric field. I'm going to get so much force. And what does force do? Okay, I guess I'm assuming here there's no other forces. What does a force do? It'll accelerate something. Okay, because when you've got something with a mass and you're applying a force to it, Newton's second law says there is an acceleration, which is why I give you the mass. Okay, so let's do this in 2 steps. The first step is what's the force? And that's F is equal to QE, like that. All right. And Q is 2 microcoulombs. All right. And the electric field is 500 newtons per coulomb, like that. Okay. And so F is going to equal. All right. So notice the units are not, well, at least for the charge, they're not MKS. Micro, what is that? Micro is times 10 to the negative 6. Okay. And so now that Coulomb there in the numerator will cancel that Coulomb there in the denominator. So this Coulomb is gone, that Coulomb is gone. And of course your answer will just come out in newtons. Okay. And so let me do that on my calculator. I'll give you a number. And it turned out to be exactly 0.001 newtons. Okay, and what is that? It's a thousandth of a newton, or 1 millinewton, like that. Okay, so that answers part of it. It doesn't answer the acceleration. Okay, it doesn't tell you the acceleration, but it does tell you the force. Now, how do you get the acceleration? Well, if you've got a force on a mass, F is equal to ma. Okay. Now, technically, that should be the net force, but like in the context of this problem, I'm not mentioning anything about gravity or anything like that. Okay, so let's just assume that the electric force is the only force of interest in this problem, the only force that's causing the acceleration. So F is equal to ma, and I'm asking for a, so a is equal to F divided by m, and F we already have as I'll write it in the MKS form like that. And what's the mass? The mass is 3 grams, like that. Okay. And so the mass is a bit tricky because it's in grams, but grams is not the MKS unit. You want it in kilograms, okay? So in kilograms, if you kilo is like multiplying by 1,000. So if you multiply by 1,000, you got to compensate by dividing by 1,000. Okay, so I hope you get what I did there. What I did here is, you see, there's no other. There's just 3 in grams. Well, if I put a kilo in there, that's like putting a 10 to the 3 in there. Okay, maybe I should do it in 2 steps. So I put in a 10 to the 3. I can also put in, whoops, multiplied. Okay, if I put in a 10 to the 3. We say, well, why did you put that in there? Well, I got to get rid of it, so I got a 10 to the minus 3. 10 to the minus 3 times 10 to the 3 is 1. Okay, so it's like multiplying by 1 there. Okay, now the 10 to the 3 there, I can say, well, 10 to the 3 is 1,000. That's just kilo. Okay, so there's your kilogram, and there's the 10 to the minus 3. Okay, so this is a little bit different way of, like, I don't know, of converting units. Okay, we could always use the magic fraction technique, which, like, the very first lecture I ever gave you last semester. All right, so we've got this, and let me get rid of the units here like that. Get rid of those units, and this is going to equal, I'll tell you in a second. It's going to equal this, 0.33333. So let's just round that off, okay? Meters per second squared, like that. Okay, so that answers the question. All right, and it's going to give you an acceleration of 0.333 meters per second squared. Now, that isn't that big. I mean, you can compare this to, say, compare to, what's your favorite acceleration? Gravity, of course, 9.8 meters per second squared. So, you know, it's pretty small, 0.3 compared to like 10. All right, if you just round that off to 10, okay. You know, that's pretty small, but, you know, it's enough that, you know, it would, like, you would see this in a lab. Okay, so only a 2 microcoulomb force, which is easy to produce in a lab, okay, on 3 grams, which is again easy to have something which is 3 grams, and 500 newtons per coulomb. Okay, you might say, well, how might I picture that? Well, in the next question, you'll see that electric field is not only newtons per coulomb, but it can also be understood as volts per meter. And 500 volts per meter, that's also pretty easy to produce in a lab. And I know that the voltages in our house are like about 100 volts or so, 110 volts, but 500 volts is nothing, okay, in a lab. I wouldn't say it's nothing, but it's easy to produce in a lab, okay? And that means a 500 volt difference over a 500 volt change over a distance of 1 meter. That's pretty easy to produce. And yet, with, you know, these relatively small numbers, you're going to see an appreciable acceleration, okay, of that 3 gram mass. Okay, and so there you go. All right, it's a manifestation of the fact that electricity is a pretty big force compared to gravity. Okay, let me see if there's any questions in the chat here. All right, no questions, and let's continue to our very last problem, problem number 8. So this is the bigger problem, okay? And I don't know if I want to draw a picture of it. I think it's pretty clear. This is a classic problem in electricity and magnetism. You've got 2 parallel metal plates, okay? And you know, in the lecture, I have picture of these, like, 2 metal plates. Okay, so you take these 2 metal plates, and what you do is you charge them up with a voltage. Okay, so basically you put a battery on it, or a power supply, a DC power supply. Okay, and what will happen is the plates will charge up, and there'll be a voltage difference between them. So what's voltage? Voltage is you know, how much potential energy per unit charge something has if it goes from one plate to the other. Okay, so it's not the potential energy, it's the potential energy per unit charge. The way you should think about it is, the more charge you have there, the more potential energy it has. It's kind of like saying, look, you know, if I'm going to drop something from a height of 1 meter, okay, I say I'm going to drop this from a height of 1 meter, how much damage will it do? Well, you'll say to me, I don't know, it depends how big the thing is. The bigger the thing is, the more damage it'll do, dropping 1 meter. And it's the same thing with voltage. You say, well, something is going to drop or cross a, say, a 50,000 volt. That's in this problem, I have 50,000 volts there. It's going to cross 50,000 volts. Okay, 50 kilovolts. How much damage will 50 kilovolts do? And I'm going to say to you, I don't know. It depends on how much charge is there. Okay, so the potential is 50 kilovolts, but the potential energy will depend on how much charge is there. Okay, and you'll see that coming out. Okay, so that's the difference between the potential and potential energy. The two words are very close to one another, and so you know sometimes students get confused, potential energy, but we've got another word for potential, and that is voltage. Okay, so all right, so we got these two parallel plates, two parallel metal plates, okay, and they're 7.5 centimeters apart, and they are charged to 50 kilovolts or 50,000 volts. Okay, what is the electric field between the two plates? You go, oh, how do I get that? So no, I'm not going to go through the theory right now, but basically the voltage is equal to E times D. Okay, so that's what relates voltage, electric field, and the distance between the two plates. Okay, so and I derived that in the lecture, so go back and if you want to see how that's done. So the electric field is basically going to equal, because that's what I'm asking. Question A, part A is, what's the electric field? So the electric field, we actually want to solve for that. Let's isolate that first. The electric field is going to equal V divided by D, okay, where V is the voltage difference between the two plates, and D is the distance between the two plates. Okay, so the voltage difference between the two plates, I tell you, is 50 kilovolts, like that, and the distance between the two plates is 7.5 centimeters, like that. Okay, so what's this electric field going to equal? Well, we got to convert everything to MKS. So kilo is times 10 to the 3. Okay, and centimeters, centi is times 10 to the negative 2. There we go. Okay, so here's our kilo, 10 to the 3. Here's a centi, 10 to the minus 2. Okay, and let me do one more line here. Whoops, what I do? Oh, there we go. Let me do another line here. Let me move the units out like this. So that was volts on top divided by meters, like this. So that's volts divided by meters. Okay, and that's another way you can express the units for electric field. Volts per meter. It turns out that a volt per meter is exactly the same. Look up here, our electric field up here was Newton per Coulomb. It's exactly the same as a Newton per Coulomb. So either you can express the electric field in terms of volts per meter or in terms of Newtons per Coulomb. Okay, and again, during the lecture, I proved that those two units are the same. Okay, or those two combination of units are the same. It's not intuitive when you first look at it. You go, how does that work out? Well, if you go back, you'll see that it works out. So, on a test, just watch out. I could say electric field, and I can ask, what is the electric field in Newtons per Coulomb? Or I could say, what's the electric field in volts per meter? It's the same number, so because Newton per Coulomb is exactly the same as a volt per meter. Okay, so what's this work out to? Well, let's see. It works out to, I'm getting a lot of 6s this evening. E is equal to that, okay? Volts per meter, like that. And of course on the test, rounding it off, 3 significant figures like that. And that 6 would round off to 7, so this will be 6, 6, 7. And then the rest of these would be all zeros. 0, 0, 0 volts per meter, like that. Okay? Or I might even write that as, because you take off those 3 there, I might even write that as 667 kilovolts per meter. Okay, because again, 3 zeros. If I move the decimal over 3, that would be in the thousands column. 1,000 is a kilo. Okay, so there you go. There's the answer. The electric field in there is actually 667 kilovolts per meter. What does that mean? That means for every meter that you moved into this field, you're traversing 667 kilovolts of potential. Okay, so I know that the plates are not a meter apart. Okay, but this is this is like a rate. Okay, and in this electric field, for every meter that you would travel within this electric field, or an electric field of this intensity, you would be traversing 667 kilovolts of voltage difference. Okay, so that answers part A. Part B, let me cut and paste it down here. Okay, what is the voltage 1.3 centimeters from that 0 volt, the negative plate? So this sometimes confuses students because the plates are 7.5 meters apart, sorry, 7.5 centimeters apart, and that's giving rise to 50 kilovolts. Okay, but if you start at the 0 volt plate, you're at 0 volts. As you move from the 0 volt over to the positive plate, which is at 50,000, you start at 0 and you slowly build up to the 50,000 volts. Okay, so there's a gradual, there's actually a linear increase from the 0 volt to the 50 kilovolts. And you say, well, how would I calculate that? It's actually this formula all over again. Okay, but now you interpret the D's differently here. D now is interpreted not as the distance between the two plates, but D is interpreted as how far into the field did we move. Okay, and so the potential difference, well, if you didn't move at all, suppose you're 0. So let me just change the question to 0. So suppose you're 0 centimeters from the 0 volt plate. In other words, you're right at the 0 volt plate. Well, what's your voltage? 0, obviously, because you're right on the 0 volt plate. And how does that work out here? Well, you've got E, which is that electric field, which is this number here, multiplied by D. Well, how far into the field did you go? Well, you went 0 into the field. So 0 times E is going to give you 0. Okay. Now, I didn't want 0. I wanted 1.3 centimeters. And so the field is, you gain, so this is the E part, you gain 667 kilovolts for every meter you walked into the field. Well, you didn't walk a whole meter, you only walked 1.3 centimeters, but that's okay. If I multiply here by 1.3 centimeters, okay, that'll tell me how much the voltage is if I've walked 1.3 centimeters from the 0 volt plate. So I start at 0 and I grow up to what point? Up to this point right here, okay, because I've walked 1.3 centimeters in. Okay, so not MKS, so let's make everything MKS. All right, so the kilo there, that's going to be times 10 to the 3, okay, and the centi here is going to be times 10 to the negative 2, like that. All right, and you can already see here how the units are working out, because you've got meters here in the denominator, meters there in the numerator. They will cancel, and you'll just get an answer which is in volts, okay, and I'll put the volts out here, okay. All right. And what's that equal to? That is equal to this number right here, okay? Or if I write it in kilovolts, 8.67, rounding off the 3 significant figures, kilovolts, okay? Now let's ask, does this make sense? So I'll try to draw a very simple diagram there. Suppose that this point right here is that's my 0 volt plate, okay? So here, I'm put another one. I'll do an ASCII diagram. Oops. Okay, so these two lines here like that, they correspond to my 0 volts, okay? Now as I walk into this like that, I'm increasing until I get to the next plate, okay? And the next plate is like right here. And now what's my voltage there? Well, my voltage there is going to be 50,000 volts or 50 kilovolts. All right. Now let's think about it. If I've walked the full 7.5 centimeters, I get to 50 kilovolts. But what if I only walked 1.3? Suppose I only walk up to this point here. Let me put a little X there like that. So I just walk up to that point X right there. Well, you're not going to be at the full 50. How much are you going to be at? You're going to be at 8.67 kilovolts, okay? So a fraction of the 50. All right, so I hope that makes sense. As you walk in, you're going to grow. You're 0 right here. You're 50 there, and so at some point when you get to 1.3 centimeters, you've hit the 8.67 kilovolt mark. If you go further, You know, if you get to the halfway point, you're at 25 kilovolts. If you get the whole way over, you're at 50 kilovolts. Okay, so it's a linear increase across there. Okay, let's continue. C, let me just cut and paste it over here. What is the voltage? 1.3 centimeters from the 50 kilovolt plate. So the opposite plate here. And so now we want to go back this way, 1.3. Well, I wouldn't say this is a trick question, but here's probably a better way to think about it. Don't think of it as 1.3 from the 50. Think of it as 7.5, which is the full way across, minus 1.3. Okay, so what's that number going to equal? Well, that number will equal 6.2 centimeters from the 0 volt plate. Okay, so what did I do here? I said, look, if we go all the way across, that's a full 7.5 centimeters. If we then come back 1.3, then effectively we've moved in 6.2. So if you're 1.3 centimeters from the 50 kilovolt plate, you're 6.2 centimeters from the 0 volt plate. Okay, now why did I do it that way? Why did I switch it to the other one? Well, because then I can just go back to this and just repeat. Okay, I'm just repeating exactly what I did above. But now, you know, when I started the 0 volt, I don't walk over only 1.3. I move in 6.2 centimeters into the field. Okay, to get to the 1.3 centimeters from 50 volts, I have to move in 6.2 from the 0 volt. Okay, and so what's this give me? Well, convert everything again to MKS. That's times 10 to the exponent 3 for the kilo. That's times 10 to the negative 2. You see that everything's going to work out in volts again for the same reason as before. And what's this number going to equal? It's going to equal this. V is equal to 41,354 volts, or rounding it off and moving the decimal over, 41.4 kilovolts. Okay, so what did I do? Well, move the decimal over 3. Here, I'll do it in 2 steps. Okay, so we've got this. All right, move the decimal over 3 here to that, and then this becomes kilo. All right, and too many decimals there. We want only 3 significant figures. So round up, and that 3 would then round up to 4. So I got 41.4 kilovolts. Okay, so that answers part C. And what's part D? Let me just cut and paste it down here. All right. So this is kind of the culmination of the problem. Okay, so it's like the where we're heading with all this. Suppose we release a 3 kilogram mass with a +2 microcoulomb charge, a distance of 1.3 centimeters from this plate. How fast does it slam into the plate? You can do this problem in a couple of ways. Okay, one of them is because if you notice the numbers, they're very similar to the numbers above here, like that. So you can actually find the acceleration, and you could say, okay, well, this thing accelerates over such a distance, and calculate it that way. The easier way to do it, though, is to calculate the potential energy, because when I release it, and I should probably say here, if we release a 3 kilogram mass from rest, if we release a 3 kilogram mass with charge that, a distance that from the initially at rest. Why did I add that? Because when it's at rest, there's no kinetic energy. Okay, so it's at rest. It's all potential energy. So when I put this 3 gram mass +2 microcoulomb charge, 1.3 centimeters from the 0 volt plate, I've given it some potential energy. Okay, you say, well, how do I calculate that potential energy? It's equal to Q times V. Okay, so the potential energy, which I'm going to call U, is equal to Q times V. You say, well, what about the kinetic energy? It's initially at rest, so there's no kinetic energy. Okay, so the potential energy of this 3 gram mass is going to be Q, which I told you is plus 2 microcoulombs, like that. And what's the voltage? Well, the voltage is going to be whatever the voltage is, 1.3 centimeters from the from the 0 volt plate. Okay, so be careful here. The voltage that you want here is not the voltage across all of them. It's the voltage at wherever you've put that charge. And I've put that charge not at the positive plate, not at the 50 kilovolt plate. I've put that charge 1.3 centimeters from the 0 volt plate. What's the voltage there? We found that in part B. In part B, what's the voltage? Okay, 1.3 centimeters from the 0 volt plate, and that's going to be, we found it to be this number right there. Okay, so we'll put that number right there. Okay, this is a typical spot where errors are made, right there. Okay, whoops, right there. Why? Because people will say, they're not thinking. They go, okay, well, I need a voltage. There's voltages all over the place, all right, in the problem. And they're going to pick the voltage of the plate, but I'm not releasing my electron, my 3 gram mass from there. I'm releasing it from there, okay? And so it's not at the full 50 kilovolts. It's at a fraction of that 50 kilovolts. It turns out we found that it was 8.67 kilovolts. Okay, so what's this potential energy equal to? All right, well, U is going to equal, let me rewrite this. So the plus we don't need. The micro, that's going to be times 10 to the, what's micro? Minus 6 micro, okay? And K, what's that? Times 10 to the exponent 3, like that, okay? And let me put the units out here. There's going to be a Coulomb there and a volt there, okay? And you go, geez, what the heck is a Coulomb times a volt? Well, it's exactly a joule. That's what you mean by a joule. A volt is a joule per coulomb, and so a coulomb times a volt is a joule, okay? And you expect that because, after all, your energy has to be in joules. So you get that U is equal to, let's work this out, it turns out to be this many joules, okay? And I'll just leave it in this form, okay? Because we're going to use it in a second anyhow, okay? So there you go. Not a lot of joules, but this 3 gram mass has a certain amount of energy, okay? Now, where is that? Well, in my diagram here, that's, I guess, where that X is. Let me just put a little bit of space there. See where that X is? That's where I've put that 3 gram mass with the plus 2 microcoulomb charge, okay? Where is it going to accelerate to? Well, the 0, by the way, I should mention here, the 0 volt, that's usually your negative plate, okay? Well, not usually. We take 0 volt as the negative plate, and then the 50 kilovolts, that's the positive plate, like that, okay? So if you got a positive charge right there, because it's plus 2 microcoulombs, where does it want to go? Well, it doesn't want to go to the positive plate. It wants to go away from the positive plate and wants to go towards the negative plate. So it's going to want to accelerate that way, okay? And that's how much energy it has. What's going to happen is all of that potential energy is going to be converted to kinetic energy. Okay, so this potential energy gets converted to kinetic energy as the positive charge accelerates to the negative plate. Okay, that's what's going on. And so, by the time it gets to the plate, all of the potential energies become kinetic, and so you can say that 1/2, the kinetic energy, 1/2 mv squared is going to equal what? Well, it's going to be the energy, right? Energy is conserved. So here, all the energy, when you first release it, all the energy is potential, and then when it gets to the plate, all the energy is kinetic, okay? And now what? Well, just plug in the numbers. We have 1/2. The mass I told you was 3 grams, like that. And I'm asking you, how fast does it slam into the plate? In other words, I'm asking you for the velocity. Okay, and that's equal to this. All right, joules. Well, almost there. We want this in MKS. Okay, and so this is going to be times 10 to the -3 kilograms, right? Like that. Because a gram is smaller, so it's a gram is a thousandth of a kilogram, all right, like that. And I'm just going to get rid of the units on the next line because why? Because once they're in MKS, you're guaranteed that V is going to come out in meters per second. Okay, that's the beauty of MKS, is that we don't have to worry about the details of how the units will cancel out. Okay, so that kilogram there and that joule there, I'll just get rid of them, and this whole expression is in MKS. Okay, now what? Well, we have to isolate V squared. So let me multiply both sides by a half first, or by 2 first. So I'll get this is going to equal, what did I do? I multiplied by 2 there, and the 2 cancels the half, and I've got over here 2 times that number there, like that. Okay, and divide both sides by this to isolate V squared. So we get, whoops, what did I do? Divided by this. All right, and let me do that on my calculator. So I give you an intermediate step there. What's this going to equal? That's going to equal that. Okay, and take the square root of both sides. You will get exactly, it's kind of nice. The numbers really worked out for this one. Exactly 3.4 meters per second. Okay, so there you go. Okay, when you release it, it'll smash into that plate at that with that velocity. Okay, so all right. If there are no questions, we're done with our review. Okay, so let me take a look if there's any questions in the chat. And looks like there's only one person hanging on. Okay, that's all right. I'm sure people will watch this later, and that's perfectly fine. But as a result, there are no questions. Okay, so let me just say good night to everyone, and that's it. All right, for our review. Bye-bye.